hands up. I assume that's a yes. Yeah, thank you. Right, so let's just get started. So here is another reminder for leaving us a self-feedback once it's open, which I believe it is now. So we're going to talk about machine learning in general. So this is the last session of the semester. We're not going to overburden your busy week 12 with everything else with another session. So we're just going to reflect on what you have learned. For example, do you have a different understanding of, shove data at this huge pile of data at this thing called machine learning and something comes out. And when you see a comic about how possibly machine learning algorithms can go wrong, do you now sort of chuckle with a different sort of a level of understanding now? So here's what we're going to talk about. We're going to take a detour and just mention something called the Dunning-Kruger effect. This is not in any official machine learning curriculum, but I recently saw it and I thought it's quite useful for me, or at least for us to think about how we think about machine learning. It's a psychological sort of effect. And then we're going to have a technical session to talk about debugging machine learning algorithms. This content is borrowed from Stanford, as you will see. It does not have derivations, but it is one of the hardest things to master in machine learning, I would argue. And then I'm going to include a brief note about communicating about machine learning, which is tied to the Dunning-Kruger effect. Again, this is also my personal choice to include this topic, and we'll talk about it a little bit. And then the last part is probably what you're looking for. We're going to do a quick run through about the topics we covered through the table of contents of the book. And then we're going to talk about release some information about the exam at the end. I'm also happy to answer questions then. So let's get started. The reason that we don't just do the course review is I feel this how to troubleshoot machine learning is a very important skill that one should not skip, right? So I hope you'll find it useful as well. So first, let's do a brief detour. The content for this is taken from a YouTube channel called Sprout. So they explain different kinds of psychology and general science concepts to the general public with attractive animations and hand drawings. I could never do as well a drawing as them, so I might as well borrow from them. So I encourage you to watch the whole video, which is about 3 minutes long. The content is about 3 minutes and something. I enjoyed it very much. So the snapshot I'm going to present here is this knowledge versus confidence curve of human learning. What this means is that when you have no knowledge, zero knowledge, you will have zero confidence on the subject, which is quite quite reasonable and expected. And when you have a little bit of knowledge, the confidence goes up quite a lot. And so at this point, one knows not a lot about a subject, but one is very confident about the subject and thinks which is both good in terms of they think the subject can have great potentials, but it's also dangerous when one's own confidence exceeds on one's own knowledge and ability of the subject. And then the confidence goes down as knowledge increases. So as you learn and learn, the student, or actually the person actually starts to doubt one's ability and confidence of the subject. And around the lowest point, you maybe become overwhelmed with the depth and diversity of the topics within the subject until you learn even more and the confidence starts to sort of recover a bit. And when you master the subject or become an expert, your confidence peaks up again. So why is this relevant? So you may ask yourself, I guess everybody's evolution on this curve is different. You may ask yourself where on this curve you might be. The other reason we're talking about this is that machine learning, like many other sort of subjects with depths, you may see other people at, for example, around this area. I would say since you have taken SML, and I would assume that you have appreciated and mastered a fair bit of the content, we are probably beyond this high confidence, low knowledge point. But please be aware that other people may be at different points of this subject, of this curve, right? Okay, so yeah, what does this matter? So it matters a lot in a large number of everyday scenarios. So this is again from the video. Assume there are three people. There's the simpleton who knows not a lot but is very confident. Back to the curve, right? There's the good student who knows quite a lot more but is not very confident. And then there is, let's say, the wise professor or the wise person who is an expert. If you imagine these three people in a debate, because of the Dunning-Kruger effect, the simpleton may actually win the popular vote, right, as this comic indicates, because he's so confident about being right, and then people, or basically the general uninformed general public, tend to trust certainty over caution, right? So the simpleton is very confident that he's right. The good student is not confident at all. The wise expert is confident, but since this person knows so much about a subject, the advice they give tend to be cautious, right? So among these three people, the simpleton tend to win the popular vote. Let's not get into politics, but I'm sure that we can recall in recent episodes of international politics where this is the case, right? And it's also worth noting that the Dunning-Kruger effect, of course, is culture dependent. So a simple example can be that if you ask a person, how well do you drive? Right, so in America, 93% of people think they drive better than the average person. Oh, how is this possible, right? So people must be quite overconfident. In Sweden, on the other hand, 69% of the people think they drive better than the average person. Oh, this is still a bit high, right? The correct percentile is 50%, right? And then in Japan, it is a cultural norm to sort of think and talk in a disparaging manner about oneself because it is seen as a motivation for improvement, right? So in Japan, this is right. The simpleton effect might be less prominent. Okay, so that's the end of the detour. Yeah, again, it's a point of reflection of asking ourselves where we sit, right? So now let's talk about something else. Some of these material are actually quite hard, but I'll give you a taste of it. So this material is borrowed from Andrew Ng. Some of you, before taking this class, might have taken his class, vastly popular Coursera or online class on machine learning, which is excellent taught. So he has this slide deck shared with Stanford Machine Learning Intro to Machine Learning class CS229. It's about debugging learning algorithms. So we've learned all of these models throughout this semester. So assume you're now given a task of building like a spam filter for emails. You carefully choose a small set of 100 words to use as features because all 50,000 words in English might be too overwhelming and too big. You implement Bayesian logistic regression, basically maximize the likelihood of the target given data and parameters regularized with this L2 regularizer, right? You implement it with gradient descent, you get 20% test error on your test set. Oh, so that's bad news, right? So spam filtering should work. And this is unacceptably high. So what should you do next? So in this class, we haven't quite asked you to do tasks like this, but if you're taking other machine learning related classes, such as neural networks or biocomputing, computer vision, or even document analysis in the next semester, you will be asked to do some machine learning system on some real data and try to improve the performance, right? So the closest we got this semester was the auto-rec assignment, but we did not ask you either to measure or improve on the performance. Some of you have written and said you were going to try and do that in the video assignment, which is great, but it's a bit of hard work. If you do that, I hope this next section will help. If you don't, I hope it will help in your other machine learning applications or projects or tech launcher or whatnot. So here is the objective function again that we're trying to maximize. So you can say, oh, let's sit in front of a whiteboard and brainstorm. So you and your teammates got a number of ideas, right? So you can try getting more training examples. You can try a smaller training set of features, smaller set of features to train, or you can try a larger set of features to train, right? How good is the 100 words? You don't know. And you can change the features, right? Try to use the email header versus email body features. If you have used one, maybe try the other, or maybe combine the two. And you're wondering whether gradient descent is delivering you the desired result, right? Should you run it for longer? Should you try not gradient descent, but Newton's method? Or should you try a different value of lambda? Or should you try using a support vector machine rather than logistic regression? So assume you've written all of these on the right board. You may say, oh, all of them look reasonable, right? This approach might work, but it's largely a matter of luck, right? So you stare at this, you might say, well, this is really an engineering task if you go and try each of these, when you end up fixing what the problem really is. So the argument here is, rather than trying all possible reasonable options, maybe you can run some diagnosis, design some measures, or do some plots to figure out what the problem could be. So here's what we would argue the better approach, right? So we run some diagnostics to figure out what the problem is, and then fix whatever the problem is. So the phenomena, not the problem, is that Bayesian logistic regression's test error is high. You suspect that the problem can be overfitting or high variance, or underfitting or high bias, right? Too few features to classify spam. So once you've recast the problem in this way, you can say, oh, if the diagnosis, we need to diagnose high variance versus high bias, I know how to do that, right? Early on this semester, we looked at learning curves. So high variance, the symptoms of higher variance is that training error will be lower than test error, much lower than test error. And if it's high bias, then training error will also be high. So here's what we meant pictorially. Right, so note that these learning curves are graphed on more and more training data. So if so we look at the gap between training and test errors, right? So if training error is low, oh, okay, let's go. I hope you can hear me right now. Okay, and great. Thanks for the thumbs up. Right, so this is where we were before the teams crashed, right? So if there is a big gap between training and test error, what is big is like data set dependent and metric dependent, right? So, and your desired performance here, you know, it's possibly high variance, right? So, and you can see that test error is still decreasing as M increases. So maybe larger training set might help. And in here, when we say test error, what we really mean is on validation set, right? So you should only look at learning curves on validation sets. For those of you who have taken Intro to ML, the view of machine learning data sets is, of course, like training data, validation, and test. And the test set, this is off limits. And in fact, you can also basically rotate through the training and validation splits. There are other notes about this because you might have leakage, right? So if your data is time-stamped, do you want to train and validate on the same time period, or do you want a different split, right? Anyway, so we're talking about validation error here. And then, yeah, the large gap between training and validation suggests there might be high variance. So more training data might help. So here's another kind of stylistic learning curve, right? So if the model has high bias, then training and test error will be pretty close, right? So if test error or validation error is 20%, then training is also close to 20%. This means that sticking with the current model and features, and also this performance has pretty much saturated with respect to training set size. A lot of times these need to be measured in log scale. That means more data wouldn't help. this suggests that you might want to change the like feature or the model being learned. Right. So this is what we just said. If you give the model more training examples, you will fix some of the problems in high bias. We can try or high variance. We can try a smaller set of features which will fix overfitting to an extent, right? So this is also fixing high variance. We can try a larger set of features that might fix high bias, and we can try different features in different parts of the email, which can or could also fix high bias, right? You can come up with basically, once you put it into the terms of bias and variance, you can come up with other ideas that might fix high bias, like try a neural network and so on. And then these other ideas are a different kind of ideas. It basically it decomposes the model into different parts, basically model specification and the optimization component. So bias and variance is one common diagnostic. It's by no means the only diagnostic you can use, right? So for other problems, it's usually up to your understanding, your ingenuity to construct your own diagnostic and figure out what's wrong, right? So in this particular case, we're talking about diagnosing errors versus the quality of the optimization or gradient descent. So in here, suppose we also contrast logistic regression with support vector machines using a linear kernel. These two are fairly similar models. They are both like linear combinations of features. And you observe that, say, Bayesian logistic regression gets 2% error on spam and 2% error on spam, on non-spam. So if we get basically 2% of non-spam classified as spam, oh, that's a lot of entries. So that's not very good. And SVM, on the other hand, it gets 10% of error on spam and 0.1 error on non-spam. So this is acceptable, but on a different trade-off point, right? But you dislike logistic regression. So what do you do next? So you might ask whether gradient descent for logistic regression is converging, right? The most direct way of looking at this is to look at the objective function J of theta, which is presented a few pages ago. All right, it's here, right? The regularized likelihood. So let's look at this. And then over different iterations, the objective rises, and you're not sure if it plateaus because, well, as we know, the optimization basically, the objective improves in different scales, first very rapidly, sometimes oscillates a bit, but then it could still be improving. So what do we do? And also notice that we can't plot this particular learning curve over different data set sizes, because if J of theta is not comparable for different training sets. So now do we do? We can ask, are we optimizing the right function? And we can ask, basically, we can try and diagnose the optimization with the error metric that we care about. So let's say we care about weighted accuracy, right? And the weight is W is higher for non-spam than for spam. Basically, we don't want too many false alarms. And here's the objective. So the weighted accuracy is called alpha of theta for a given set of parameters. And then the objective is called J of theta. And for an SVM, this is the objective with, like, we solve this constrained algorithm optimization problem by performing grid search on hyperparameter C. So we noticed that actually, so for the primal problem for SVM, we could like imagine we have the same set of weights for like feature weights for and use it for logistic regression, which is not necessarily optimal weights, but it's a valid weight. So we look at, for example, the set of parameters being learned using Bayesian logistic regression versus SVM. We see that SVM outperforms Bayesian logistic regression in terms of weighted accuracy. And then we plug in. So obviously SVMs are finding a more preferable solution in terms of the end result evaluation metric. So we plug in the weights from SVM into Bayesian logistic regression and ask what the objective function for the Bayesian logistic regression is. So if the objective is larger, in this case, we're maximizing, right? So the objective by taking the SVM weights is actually better than the objective by taking the Bayesian logistic regression weights. That means, oh, we are not maximizing, like, or at least not finding a good maximum of this J of theta that we would like, right? So this is basically summarized in case one, right? This means that theta of Bayesian logistic regression fails to maximize J. And the problem is with the convergence of the algorithm, right? So the problem is how we have conducted the optimization. So maybe like we try a different optimization module, let's say with momentum, without momentum, adjust the learning rate, or have multiple random starts from different places and see where like where the optimization improves drastically. So at least this narrows down the problem for us to debug. This scenario here might be contrived, where we can plug in the weights from SVM to debug logistic regression. In a lot of models we learn, especially generative models, what we often do in my research group is that we, on some synthetic data, we come up with weights, right? Or even use the weights that are used to generate the data and then see where the optimization leaves it. If it drives the weights off into somewhere far away and we start from the correct weights, then it's not a good sign. Either the model is misspecified or the optimizer is not doing the right thing. But if it starts from the correct weight and just stays in the neighborhood, not necessarily in exactly the same point because of finite sample effect, then the optimization is probably doing okay in that particular case. So in the case number 2, so if we contrast this, we still have SVM achieving better accuracy. And then in terms of the objective function, the Bayesian logistic regression has larger or better objective. So this means that Bayesian logistic regression succeeds at maximizing J of theta. But in this case, you will find yourself, right, okay, so the optimization seemed to be okay, or there's nothing obviously wrong with it. But why does it still sort of do worse on the weighted accuracy? This means that the objective function is the wrong function to be maximizing if what we really care about is the evaluation metric alpha of theta. So the problem now is with the objective function of the maximization problem. So this also happens a lot. Basically for machine learning in practice, I could talk for an entire session about different evaluation metrics. So there are evaluation metrics that really correspond to a real-world task. In this spam case, it's close enough. There are also surrogate metrics that's sort of just feasible to compute and it approximates the real-world tasks. For example, in machine translation or natural language processing tasks, such as summarization or image captioning, there is the metric called blue and rouge. Blue and red, essentially, they are basically n-gram metrics that are used to approximate the quality of sentences, because measuring sentences is quite hard. So these examples abound. It's a warning that basically choose your evaluation metrics carefully and then still include it in your debugging processes. So that's basically the second half of the your brainstorm list, right? So if the problem is in the optimization algorithm, then try, for example, run gradient descent for longer and try different optimization methods. And if sometimes optimization objective is not that complex to fix, it could mean that we have not done the hyperparameter sweep appropriately, and then the regularization constant lambda is off. Or maybe we should be using SVM after all. Or maybe try kernel logit regression, and so on. So that's basically the main section, right? So Andrew also included this attractive example of how he debugged it, how to debug a more complex learning system. So Andrew Ng's PhD thesis, I believe, and also for a while at Stanford, he worked on autonomous flight in a helicopter using reinforcement learning. So this is a 32-pound helicopter with payload, right? And the goal is to learn to ask the helicopter to learn to fly itself. Of course, but not by crashing itself to the ground many times, but doing so in a simulator, right? So you build a simulator and ask the helicopter to control itself so that it stays in the air. Let's say you choose a cost function, which is, say, some square distance between the desired position and the actual position. And you run reinforcement learning to fly the helicopter in the simulation and try to minimize the cost function. Now we're minimizing J of theta. Suppose you do this and the resulting control parameters learned by reinforcement learning gets much worse performance than your human pilot. So what to do next, right? So for human pilot, the position, you can't exactly track the position all the time. There is still an error term, right? So what do you do? Improve the simulator or modify the cost function, or is your reinforcement learning algorithm wrong? So applying what we learned, right? So the problem or the phenomena is that a controller, given the RL parameters, perform poorly. So if we suppose that the simulator is accurate, right? So in normal conditions, let's say it's not too hard to write a Newtonian physics simulator, and assume the RL algorithm correctly controls the helicopter so as to minimize J of theta. You could actually verify that using a simple trajectory for the helicopter, right? And then we can, we also assume that minimizing J of theta correspond to correct flying, basically minimizing the square distance of coordinates is the right thing to do. If all of these three are correct, then the learned parameters should fly well. And now we basically pick apart the three components and see which one could go wrong, right? So if this set of theta flies well in simulation but not in real life, then the simulator is missing something. Maybe there are missing components of the Newtonian physics that you haven't taken account of. And then If we also have access to a human-controlled policy, basically human-controlled set of parameters, set of human, and if our objective for the human-controlled parameters is a lot less or a lot smaller, a lot better than the reinforcement learned one, then the problem is the reinforcement learning algorithm not finding the correct minimum in J of theta, right? So it's failing to minimize the cost function. And if, on the other hand, the human, so the IL parameters are actually better in terms of the objective function than the human flight parameters, then the algorithm, reinforcement learning algorithm, will be correctly minimizing the cost function. It finds a spot that's even better than the human-controlled flight. Then actually minimizing the cost function doesn't really correspond to good autonomous flight. So this last case actually happens a lot in reinforcement learning, right? So if there are plenty of examples online where you try to teach a stick figure to walk, but what it does is that it stays upright, that's all right, but it learns to hop on one leg or something. Which is not the desired behavior, but it's still minimizing the objective function. In that case, there's a lot of literature on IL reward mismatch and so on. So this example basically goes to show that breaking down our problem into a set of separate concerns that completely covers the workings of our algorithm, the entire system, and then try to basically come up with diagnosis for each of these components will help. So very often you will need to be creative and come up with your own diagnostic to figure out what's happening. Even if the learning algorithm is working well, you might also run diagnostic to make sure you're understanding what's going on, right? So this is useful for understanding our application problem, writing a research paper, in general, instead of saying, here is an algorithm that works, it is a lot more interesting to say that here's an algorithm that works because of component X. And here are some evidence, right? So I would argue making a machine learning algorithm perform well on the validation set or even test it is not the goal. It is the understanding that will help us to know, for example, what has gone right, both as an engineer and also as a researcher. And this is how we accumulate knowledge about either the domain or about a research problem. So if you're writing a paper, then you're definitely expected to have this component, right? So I would argue, for example, in my research group, no paper goes out without an interpretation or explanation about why things work. So that's pretty much all we needed to say about debugging machine learning algorithms. So Andrew Ng's slide deck also has a whole section on error analysis that I'm not going to go in. So if you have done a few benchmarks, you will know ablation studies and so on. In terms of really debugging and implementing machine learning systems end-to-end, there's also another set of very attractive notes. I love it very much, from Christopher Rowe, who builds knowledge acquisition systems and teaches, again, CS229 in Stanford. So his summary is that machine learning systems are split into 7 steps, right? And every single step could go wrong. So for example, acquiring data. So what do we encode in data can already encode social technical biases and what our preconception of the problem includes. And this particular step 2, looking at your data after every step, echoes what Andrew said, right? So we have to understand what is going on, and there is no better way of understanding than plotting our data and then plotting our predictions, trying to visualize the errors and look at what went wrong and where things break. You may think that creating training, development, and test splits are textbook material, but as we said, you can have leakages in there. For example, if you're building a recommender system, you may not want the same user to be both in the training set and the test set. That will lead to like inflation of performance metrics. Creating and refining a specification for your machine learning algorithm is also part of the problem. Do you want a binary label? Do you want uncertainties? Or do you want something else? So build a model from the simplest that works to the more sophisticated. The larger and more complex model is not necessarily the best thing. So measurement, as I said, like evaluation metrics is a topic on its own. So be careful about what you choose. And then rinse and repeat, right? I do highly recommend you go through this other set of slides. It's kind of long, but it's very visually attractive and nice. I also believe there is lecture videos of these online as well. Just dig around in the Stanford course website. Another thing that Christopher's lecture slides also mentions, and also a recent NeurIPS paper, basically, I believe this is NeurIP 2015, can verify. Here is a view of where machine learning code sits in the entire system that uses machine learning. Right. So in a real world machine learning system, or if you're writing, let's say, machine learning code for computer vision or for recommender systems for a website and so on, your machine learning code is usually, I would say, anywhere between 5 to 10% of your code. Because the rest of your code and software system are dedicated to configuration and configuration management, collecting data, extracting features, verifying your data, wrangling the data so that it actually becomes the shape and size of what the machine learning code is willing to take, managing machines, analyzing and monitoring performance and results, like serving your results to, let's say, like your audience on internet, and monitoring the whole thing to make sure the software system runs and give you an alert or the buzz if anything goes wrong, right? What this says is also that machine learning is also a component that is where it's easy for you to accumulate hidden technical debt, right? What that means is we shouldn't think about machine learning code in production as a one-off thing, right? Once we use a particular machine learning algorithm, all of the corresponding input, output, and monitoring code will need to change, right? So the take-home message from here is that machine learning code is not a cure-all. Instead, it's a sort of a credit card, technical credit card with high interest rate. Right. So machine learning algorithm can be brittle, and there are software engineering practices that can be used to address basically the engineering of the system around all of the machine learning code. Of course, this is not to say that the deep or the depths that we have gone into, it has no role to play. So having a deep understanding of the machine learning code will not only help us to choose the better and design better models, but also understand exactly when things could go wrong and where it could go wrong, and also design and maintain the surrounding systems in corresponding to that. So that's pretty much what I wanted to say about debugging machine learning. Is there any questions? If not, here is another one slide about communicating in AI and machine learning. So I thought this is a good thing to share with the class, because now that you have learned your first in-depth machine learning class, well, going back to the Kruger effect, you might feel that you are now qualified and to comment on what machine learning do and cannot do for your friends, your family, or your boss at work, or your boss's boss at work, and so on. So whether you choose to communicate about AI and machine learning in general, it depends on your worldview. Feel free not to, right? So in case you do, here's a few tidbits that I would like to share with you. Again, I borrowed them from Professor Michael Woodridge from Oxford. He gave this as part of Triple AI, like the top AI conference keynote talk this year. So as you know that there is still lots of discussions about artificial intelligence in the media. You wonder why, right? So it is good that they get this technical area gets so much attention in the last 5 to 10 years, right? So the screenshot here was like in 2014, Stephen Hawking, the late Stephen Hawking, arguably the most famous and brilliant like astrophysicist, he warns the public that artificial intelligence could end mankind, right? So when a person like Steve Hawking or Elon Musk says something like this, the press takes notice. Then what do you tell people about it? And what should you think about it? Yeah, feel free to make up your mind. I wouldn't say any of these things that I say is cast in stone, and it certainly changes over time. So in public communication, the word AI is often conflated with machine learning. It's a subfield of artificial intelligence. And SML, or machine learning, is in the press so much, in part because there has been real progress, right? It's driven by a number of factors, right? So scientific advances, basically insights on how to learn complex model, basically deep learning well, to prevent overfitting and so on. And there is, in the past 2-3 years, there has been theoretical understandings of this as well, so which is great. So these are scientific progresses. In part, it's also driven by larger, not necessarily better data sets that are readily available, say, think millions of images, gigabytes of text, and so on. And they're also cheap and easily available computational power, right? So the advance of GPUs and graphics cards that can be used to train neural networks has helped a lot. And the fact that you don't need a server farm to train or tune a large neural network has also helped a lot. So the view I would like to share, which is certainly my own, is that these advances are narrow. And they don't necessarily deliver the grand dream of AI or having an intelligent being that can sort of end mankind or outperform us. Because if you think of it, despite AI has beaten humans in almost all like board and like chess and Go games, and also to some extent in strategic games such as Texas Hold'em poker, doing those does not deliver true intelligence because it still requires a strict specification of the task within a closed environment. if you ask a AI or a robot to basically pour me a cup of coffee, they still cannot do it. One part of this dichotomy of what AI was like has superhuman capabilities, but on the other hand, it cannot do simple things that we can do in daily life, like a 5, 6 year old, is like only one of the many factors is what I call the unloading of the word uncertainty, right? So one is the basically probabilistic nature of real world events. Basically, what the opponent will move and what fraction of chances this move will lead to a winning position. The other one is what I call what is relevant in the real world for a particular given task. For example, if I'm pouring coffee, the shape of the mug is relevant. The weight of the mug is relevant. But like whether there's another person in the room is not relevant unless the person comes sort of in the path of myself and the coffee machine, and so on and so forth. You can think about many real world problems as basically the uncertainty is in the many different factors that one cannot readily capture it on a chessboard. Right. There are many other open questions I'm not going to get into, but all in all, the AI abilities, they are narrow on a basically precisely defined problem. We can imagine AI to do a lot in machine learning and beyond. For example, in planning problems, in scheduling problems in airports, and like large train stations and so on, and scheduling university classes. Those are where AI does well, right? But pour coffee or taking care of the elderly, the sick, it does not. I would say, well, look at the media hype. With a cool head, AI advances are real. Machine learning advances are real and exciting, but they are not magic, right? In particular, we can be aware of these long-term speculative concerns, such as the future of mankind, and I feel that a healthy dose of such thinking is very good for our basically own perspective and also the long-term growth of AI as well. But it shouldn't distract us from near-term worries, such as the bias of the algorithm, the brittleness of the algorithm, like employment prospects of different industries under AI, and for example, climate change, which is the real threat. And if we don't do something, I guess now or 3 years ago, things are going to get really bad. And if things are getting bad, what should we do? I would say that we should also guard ourselves against a simplistic view of the social implications of AI, the fairness and transparency and accountability, right? I have two examples here. So you might say, so the symptom here is back in 2015, a software engineer in the Bay Area pointed out that the image recognition algorithm that Google puts in Google Photos wrongly classifies his Black friends as gorillas. So that's terrible. It's a racist algorithm. And to this day, it's not fixed, right? You can say that maybe there isn't enough training data for that distinguishes like people of a particular race or some races and the classes we don't desire them to get classified into. But fixing data set is never the only answer, right? And Google, with all the data set again it got, has not fixed this algorithm, and the class gorilla simply is not offered, right? And And the other example what I would share is Amazon. Scraping is it has had a secret AI recruiting tool that screens resumes. Like in a large firm like this, you can imagine there is lots of demands for hiring, and then there is lots of people interested in applying as well. So the reason that it had to essentially scrape this secret algorithm is because it perpetuates biases and stereotypes. The recruiting engine, machine learning engine, did not like women. You may say, well, yes, because there is not enough women in the software engineering workforce, therefore it does not see enough training data. But this is a chicken and egg problem, right? If you want to solve this by machine learning alone, you might say now we need to supply more women's CVs as qualified software engineers. But if without enough women in the position, there isn't enough data. And then it also begs the question about what is fair, right? So what can one do about historical inequalities across race, gender, and a bunch of other attributes? Unfortunately, there is no short answer to this, and computer science or machine learning alone will not provide an answer. So there are a lot of research literature on basically fair machine learning algorithms, especially in classification. Um, I would say they address part of the problem, but certainly not the entire problem, because for example, racial inequality in criminal justice is such, especially in the US, is such a problem that's rooted in historical injustices. And for example, one argument could be to fix the disparity or basically have racial parity currently, but that does not address historical inequalities. So what is fair is sort of an algorithm, like a concern that can be encoded in algorithms and is often implicitly encoded in algorithms, but is not something that computer scientists or machine learning researchers and engineers could solve alone, right? And it is important, right? So lessons from histories outside of computer science abound about how historical inequalities have led to terrible consequences, right? So in the car industry, the crash test dummies, basically dummy figures with humans, are made as men's figures. As a result, the cars that we drive every day are actually less safe for women than for men. In a lot of medical research that starts out from mice models, the mice models are, most of them are based on male mice. So as a result, like female, not just humans, but also all the way to our animal primitive are like much less understood. And the reasons for including only male mice was historically that they're more convenient because they don't have biological cycles, which is, yeah, not a great reason for excluding half of the population of something. And then there are many clinical studies that underrepresent minorities. For example, the level of pain in African Americans are like have been understudied for a long time. As a result, the medical insight for minority groups are much less accurate than the majority group. So that's all what I wanted to say about basically perspective of machine learning algorithms. I hope I've offered a few tips and things that you can, principles that you can go and use. I've also offered a few warnings about what we learn and what we think we know. Is there any questions so far? Okay, if not, we'll just do a run through about what we the technical content of this semester and what the exam looks like. So we basically covered machine learning from scratch. We looked at what machine learning is. We looked at the foundations of that machine learning builds on, basically probability theory. What are the key quantities, expectations, covariances? We looked at the sum and product rule of probabilities. We looked at the Gaussian distribution, what a Bayesian view of curve fitting looks like. We briefly talked about model selection, the curves of dimensionality, decision theory, and we, in terms of information theory, we talked about chaos divergence. But in this class, we did not cover what information entropy is, and I won't hold you responsible for that particular one. So more background, we looked at a number of commonly used distributions, in particular beta distribution, Gaussian distribution, including conditionals and marginals, and Bayes theory for theorem for Gaussian variables. We looked at mixture of Gaussians and maximum likelihood estimation for the Gaussians, and also a mixture of Gaussians. We did not look at the exponential family. We did look at kernel density estimators and nearest neighbor methods for non-parametric methods just before kernels. We spent a fair amount of time on regression, basically looking at different regressions, objectives, and how they connect to each other. We looked at the Bayesian view of linear regression. We also looked at classification of a few different ways. We looked at learning discriminant functions for two and multiple classes. We looked at least squares for classification, why it doesn't work. We didn't look at Fisher's linear discriminant in depth. We just say it's a different objective. We did look at the perceptron algorithm and how we basically perform updates in perceptron. And we did later connect it to neural networks. We looked at probabilistic generative models for continuous and discrete output. We didn't look at that for the exponential family. I think that's fine. We also derived the logistic function using probabilistic generative models. We then used that to learn logistic regression, right? We did not quite look at Bayesian logistic regression. We did say you can put a regularizer to it. And the way we now learn logistic regression is via gradient descent, and we didn't look at iterative related least squares. So in neural networks, we looked at basic neural network architectures, connection to perceptron, and how we optimize them using gradient information. We looked at issues of that the gradient can potentially run into. We basically talked about optimization in general and global, the notion of local and global optimum. We looked at error backpropagation as a concept. And we really briefly looked at autograd, right? So we covered a few intuitions about regularization in neural networks in the lecture and workshops. We did not cover all of the regularization tricks. And in fact, some of them are not commonly used now, for example, explicitly incorporating invariances using weights. In the neural network section, we also looked at nonlinear latent variable models such as autoencoders. So the next chunk of content we covered is basically the beginning of kernel methods and the beginning of maximum margin classifiers. We looked at dual representation in classification and regression, and we looked at constructing like what are valid kernels. We looked at Lagrangian multiplier in some detail, and then we applied it to derive the support vector machines in the formulation in the dual space. Right? We briefly looked at SVM super regression. The last chunk of material that we covered are roughly, say, probabilistic graphical models. It covers, like, depending on how we call it, about 4 chapters towards the end. We looked in detail, we spent more like 3 sessions talking about graphical models. We talked about 3 kinds of graphical models: Bayesian networks, Markov random fields, and factor graph for inference, in particular the sum product algorithm. And we talked about the notion of deseparation in detail and then how we reason about conditional independence. We actually covered mixture models and expectation maximization first, but this is a simple example of graphical models. Basically, we have data X and latent variable Z. We reuse this structure a lot, including in HMMs. So in mixture models, we covered k-means clustering, and we covered mixture of Gaussians as a probabilistic means of k-means clustering, basically the connection between the two. We looked at the expectation maximization algorithms 3 times. And we did look at why EM algorithm improves the objective. As this part of this probabilistic graphic model chunk, we also looked at sampling methods. We looked at basic sampling algorithms, rejective and important sampling algorithms. We also briefly talked about Markov chain Monte Carlo. Basically, how do we move through the sample space rather than just jumping through the sample space in the hope to get a better sample. We also looked at Gibbs sampling as a special case of Markov chain Monte Carlo. As coordinate-wise update. In terms of continuous latent variables, we looked at PCA in some detail. We looked at kernel PCA in our homework. We looked at, well, this chunk of content on autoencoders is actually in the PCA chapter in the book. And in terms of sequential data, we applied essentially the same latent variable model, but stretched out over time. We looked at inference and learning of hidden Markov models and the definition of hidden Markov models. So this is, for me, the contents in chapter 13 is sort of synthesis material for, you can think of it as tying the mixture models, the graphical models, and the inference all together. So this is it. So this is a very quick rundown of what you know. And back to the Dunning-Kruger effect video, the wise man Socrates said that, well, I know I'm intelligent because I know nothing, because there is a lot more to learn in machine learning. But rest assured that when one starts off in a subject, you might be scared of all the things that there is to learn. But at this stage, hopefully you have overcome some barriers and learn something. And we can optimistically believe that we're on our way to the wise man in the process of learning. So learning remotely is quite hard. And I hope you guys will all give yourself a round of applause for persisting through the semester. And there is basically a little, well, like 2 more weeks to go. So finally, the exam, right? So, oh, yeah, thanks for that, for giving each other the applause. So I'm sure a lot of you will want to see this slide. The same content will be posted to Piazza as well. As you saw from timetabling, we will have an online exam on the 8th of June, Tuesday, afternoon time. It's set to start 2:40 rather than 2 o'clock or 2:30 because the exam office wanted to scatter the support of Wattle and then basically distribute the load a little. So workshop as a Wattle quiz is being worked on by us, the lecturer and tutor team. So here's the specs that I'm able to give right now. So it's an individual assessment, it's an exam. So it's not a paired or team assessment. You're required to sign an honor statement, basically typing your name, saying that you're completing this exam on your own, and what is being submitted consists of the intellectual output of yourself and no one else. What this means is that it's open book and open anything, almost. You're welcome to use the textbooks, notes, Python, use online material if you have time to look at them, or do internet searches if you have time to do so. It's not okay to discuss with your friends, your peers in the class, or post the question somewhere for others to help you. I hope this is common sense, but it's worth stressing. And the coverage of the exam is of the content we just talked, ran down in the last 10 minutes. What I would recommend that you may need is you could need a calculator app or have a Python window open. You might need pen and paper for simple derivations, and you might want to keep a camera app handy to upload or take a picture or upload your pen and paper derivations. You're also welcome to type in LaTeX as well. So just keep in mind, whichever way you do, it needs to be clearly legible for us to grade. Otherwise, there might be penalties, or if we can't read, you don't get the mark. I would say the exam will be somewhat challenging because it is intended to sort of correlate with the level of knowledge people have gained in a semester. We would rather that people spread out. So I'm not too concerned if the absolute grades are low because we can always scale up. What I would like to avoid is that everybody scores 85% and then at the end, and then because there will be moderation process at the end by the school, not by individual courses, I would not want to having to deduct 2 points from everybody or X number of points from everyone because the assessments are too easy. That has happened before to other courses I teach and other courses that other people teach. So I would rather be in a position to scale and moderate up than down. Let's see how we achieve that. Of course, if everyone does very well in the exam, I will be delighted that everyone gets above 80, and then I'll try and stand and defend everyone's performance in front of the moderator meeting. So that is to say, good luck. It will be somewhat challenging from our estimates. So we are budgeting basically about more than half of the questions should be multiple choice or simple calculations where you type a number at the end. And then a smaller fraction of the questions will be long calculations or proof or some derivation. It won't be very, very elaborate proof, we would say, because of the time constraint. You only have 3 hours to do the exam anyway. So, and the reading time, 15 minutes, is factored in. So since everybody is doing it, wherever you are, use the 3 hours and 15 minutes, right? So I would say there will be bespoke questions, such as those you have seen in the quiz, and then applying and reasoning, applying what you have learned and reasoning about real world data, and then connecting them, right? For example, we might ask you, oh, here is like 3 training points. And if you do a like linear classification with this particular formulation, what would you get, right? And we might say, oh, here is 3 training points, and here's where the perceptron sits. If you do one update, where do your decision plane or where do your network moves? Well, what's your network weights in the next step? So these are some of the simple questions. And then we will have questions to minorly extend what is taught, right? So if we say, given that you have learned linear regression, the expression of linear regression, what if we have linear regression but with different weightings on the different training examples? What will we get, right? So you might need to work a bit on like towards that kind of question, but not too much. So I would say the length of 35 to 550 questions is, it's a bit long. And my recommended strategy will be, well, you do a question, do it once and try to get it right, because you may not have time to get back to it at the end. And strategize, right? So maybe like tackle all the questions that you can do, and then come back and spend more time on the harder questions. So to this end, we're providing 2 sample exams to help you. They're already posted on Piazza resource page. I will link it to the Piazza post as well. So there is 2019 final exam and also a 2020 exam, but it wasn't used because of last year switching to online learning of last minute. I would say, okay, the scope of these exams and content are different, somewhat different. For example, there were questions about approximate inference. So yeah, we don't have that. There's a few examples like that. So I would say, how should you use the sample exam, right? So you can expect the style of questions to be similar, but the question formats will differ because SML course hasn't had a Watto exam yet. And if this is not your first semester in the ANU, you would have had other online Watto exams. So right, adjust your expectations. So our intention is also that some of these multiple choice and calculation questions can be auto-graded so that you don't have to painstakingly elaborate everything. Right? Hopefully that makes life easier for everyone, both the person, our team grading it and yourself. And then, no, we do not release solutions for these sample questions. There is no need to ask. So that's all. I will just pause for a bit. I hope this addresses. Right. So, yes, the questions, the exam questions are to be answered on Watto directly. Is in the form of Watto quiz, answer directly on the quiz. Basically, right, so we did our quiz on Grayscope, but it's basically similar. When it's a multiple choice question, you'll get different radio buttons or checkboxes to click. Then you just click through them. And Watto automatically saves your progress. And you get 5 minutes grace period to submit anyway at the end. So basically, in case you don't submit, Watto will also submit it for you. So that's the advantage of relying on Watto to track your progress through the long exam. I hope that helps. And for questions that require typing or so, you can upload either a picture or just type. Either way works. I would say upload as you go. So the question is, do we have extra time to upload your answers to Watto? So the exam is 3 hours and 15 minutes is all included in there. And everyone has the same time. Another question. Good question. Communication channel during the exam. We imagine it will be Teams. Basically, about 2 of us will be available, and we will announce it closer to time. Next question. So, will there be negative marking for multiple choice questions? Especially if there is more than one correct answer. I Let me double check with Watto settings, but my short answer, my intention is no, right? Suppose, let's say if a multiple choice question is worth 4 points, and then there are 4 options, 2 of them are correct, 2 of them are incorrect. So basically your correct or incorrect choice for each of these options will count as 1 point. I need to verify exactly how we implement that, but that's the intention. So you won't basically lose points for the other questions if you do a multiple choice question wrong. I hope that answers the question. Huh. There is not a strict distinction that the multiple choice questions are easy or easier. I would say there are certainly easy multiple choice or true false questions, but I wouldn't say all of them easy. And I also wouldn't say that all of the calculation questions are necessarily harder than the multiple choice questions. So we will try to sort of sort the. So there's basically 2 ways to sort the exam questions. One is by topic, the other one is by format and perceived difficulty. So we'll try to do some sorting to help you, but I do not guarantee the sorting will be monotonically increasing in difficulty either, because also difficulty is such a subjective thing. When something is more difficult for you, it might be less difficult for others. What I will intend to do is to have the beginning section somewhat easy or not too hard to give people a warm up, and afterwards you can, go at your own pace. I hope that helps. Yeah, good question. So we are working on assignment to grade assignment 2, and we expect to be able to release it before the final exam so that you have feedback for assignment 2. That's pretty critical in my opinion. For video assignment, no, we will not have enough time to grade them as well if we grade, we aim to release assignment 2. So I hope that answers the question. Good question. I do not intend to ask you to write code on Wordle because we can't auto test it. Although you might choose to, for example, use Python to generate some of the answers, and that's perfectly fine. But we don't need to see your code. Unlike the sample exam. Some of the sample exam have coding questions. But we don't intend to do this in the Wordle exam. Absolutely. No, you're not expected to record a video of yourselves during the exam. Yeah, I think video assignment is sufficient. I would prefer not to stress you guys out even more, so just authenticate with your Wordle credentials and focus on the exam yourself. I mentioned camera app because if you write stuff on a sheet of paper and wishes to upload, I will clarify that in the Piazza posted version. Good question. Yes, it is. Yes, this is the last time I'm going on air and to talk to you guys. We do have contact hours, and I encourage you to make use of them. I believe there's one today, there's one tomorrow, and Wednesday, and then there will be two more before the exam, Thursday of next week and Monday just before the exam. So if you have questions during studying, come to talk to us. So it's about 11:30 now. I'm just going to stop the recording. I wish everyone good luck, right? So well done sticking with the class for for the whole semester. It's not easy when we're all studying from different places and in different places. Yeah, it's another challenging year. So well done. Okay, I'll